Hello, this is Dr. Michael Hassan, the engineering doctor, and this is lecture number 42, Synchronous Counters Design Using SR Flip-Flops of Chapter 7, Counters and Registers of the course Digital Logic Design for Digital Systems or Digital Electronics. This is a disclaimer for you to read. I cite 3 references in digital logic design, however, there are many books available in the subject. In Chapter 7 contents, we covered ripple or asynchronous counters. We covered up-down counters. We covered synchronous counters. We covered design of synchronous counters using D flip-flop or using T flip-flop or using JK flip-flop. And in this lecture, we are going to talk about synchronous counter design using SR flip-flops. As a repeat or a reminder for the characteristic equation for the SR flip-flop, Q plus is equals to S or R prime Q, where Q is the present state, Q plus is the next state, and S and R are the input excitation for the SR flip-flop. And the excitation requirements table, if the present state is 0, the next state is 0, S must be 0 and R don't care. 0 to 1, 1, 0, 1 to 0, 0 to 1, and 1 to 1 don't care 0. And the flip-flop will have 2 stable states, 0, state 0 and state 1. And if we are remaining in state 0, we need S to be 0 and R to be don't care or 0 don't care, and we are remaining. If we are in state 0 and going to state 1, so we need SR to be 1, 0. If we are in state 1 and we remain in state 1, we need S don't care and R 0. And if we are going back from state 1 to state 0, 1 to 0, so 1 to 0, we need S must be 0 and R must be 1. So it is SR equal to 0, 1. And by doing this, actually we have, this table is extremely important in counter design. And unlike the JK flip-flop, we do not have a shortcut method due to the characteristic equation is not, as you see it as in JK flip-flop, is sum of 2 terms, one for the Q prime and one for the Q. Here it is S is one term and the second term R prime Q. So there is no shortcut method, unfortunately, with the design using SR flip-flops. Next slide, we will design an 8 mod 8 synchronous counter using SR flip-flops. And since it is a mod 8 counter, we will have 3 flip-flop because 2 to the power 3 is 8, 8 state or 8 counter, or divide by 8, all means the same thing. And we have the present state and next state. If we are in state 0, 0, 0, the next state will be 0, 0, 1, 0, 0, 1. The next state will be 0, 1, 0. If we are in 0, 1, 0, the next state 0, 1, 1, until we reach state 1, 1, 1. Then we go on to 0, 0, and the circle will repeat itself again. And we have to find SARA for the A flip-flop, for the SR flip-flop number A or FFA, and we have to find SB and RB for flip-flop B, and the excitations for flip-flop C. To do that, we go to the excitation requirements table just we reviewed. We look at the column A and A plus, 0 to 0. If we are staying at the same state, what we need? We need S0 and R don't care. So SA will be 0 and RA will be don't care. Okay. The same thing when we work with 0 to 0, 0 don't care. 0 to 0, 0 don't care. 0 to 1, 0 to 1, we are in the set mode. 0 to 1, we need S must be equal to 1 and R 0. So S1, SA is 1 and RA is 0. and so on and so forth. We fill out the table fully. We do the same thing with column B and B plus as the next stage. We have SB and LB and SC and LC. So we have 6 variables. We need 6 K-map, where the present state is ABC, and we have to find SA, RA, SB, LB, and SC. So we do this with K-map. See, we have SA, RA, SB, RB, SC, LC. We group all the ones that we find. So for SA, we find A prime BC, there's only one. Okay, there is no useful don't care term for me. We cannot group this because it is not logically adjacent to this. Okay, diagonally we cannot group with this. So this one is its own. For the KA is the same thing. We have only one on its own. So what we find for the RA, I do apologize, not K, it's RA, SA and RA we are here. So we find SA is A prime BC. We find RA, it's ABC, ABC. Also, we find a group of 2 for SB and a group of 2 for RB. So SB will be B prime C and RB will be BC. Very correct. Okay, for SC is C prime, group of 4. 0 will cancel with the 1, so you'll end up with C prime. Okay, on one side and 1 on the other side. So C prime and RC, 0 will cancel with the 1, 0 will cancel with the 1 for the B, so I have C. So RC will be C. So the answers are here. So once we can find the network, the logical network of the counter as shown here. Okay, so we have A prime, B, C, SA. Where's B prime? This is B and this is B prime. We don't need an inverter. We don't need an inverter. So A prime is here. We don't need an inverter. So you don't take an A to inverter, no. Take A prime to the input of this 3-input AND gate. Then B short circuit here. Then the output C is taken to this. The same thing will have A, B, C. Then B prime. B prime is here. Okay? So because the flip-flop gives me B prime and B, C and C prime, A and A prime. So we don't need to use any inverters here. Clock pulse is taken to all the flip-flops at the same time. Now, the complete design is shown, and this would be the end of a design. Any counter that you need to design with SL flip-flop, simply you go to this table. This is a very useful table, and it's necessary to design any counter with SL flip-flop. As I said, unfortunately, we don't have a shortcut method design. With this, actually, we have finished this lecture. I would like to thank you so much for listening. Please subscribe by clicking on the blue circle with the letter I inside it. Hopefully to see you soon in the next lecture. Sincerely, Dr. Hassan.